All right, question 24. What's the sum of the roots of that equation? Just need to be aware that that equation is actually Z7 plus no Z6s and no Z5s and no Z4s and so on, all the way down to -1 equals 0. And we know that the sum of the roots, alpha plus beta plus gamma, all the way up to, the 7 roots, is equal to minus b on a for polynomial. So it's equal to 0 on minus 0 on 7, which is just 0. Okay. Sum of the roots is 0. Now, the complex root of z to the 7 minus 1 with the smallest positive argument is w. Express the other complex roots of 7 to the 7 minus 1 equals 0 in terms of w. All right, so the answer is that they're w squared, w cubed, w4, w5, w6. That's the other complex roots. I think what they're saying is you've got your W, and you've got all of those, and then of course you've got the 1, but the 1 is not a complex root, right? So that's the answer. They're all your roots, and of course you've got your W, and 1 are your other 2 roots to make up your 7 roots of unity, your 7 seventh roots of unity that are solutions to the equation z to the 7 minus 1. But what, if you want to argue or explain how you get that, what might you say? Well, you might say, all right, I've got this unit circle cranking here. Now, normally when you multiply together 2 complex numbers, like say Z1 is R1 cis theta and Z2 is R2 cis phi, right? When you go Z1 times Z2 normally, you multiply together the 2 moduli, the 2 sizes of the complex numbers, and you're going to add the arguments. So it's going to be cis of theta plus phi, all right, normally. Now, in this case, these are complex roots of unity that we're talking. So they're all going to have a mod of 1, right? Each of the roots is going to have a mod of 1. So if I multiply a root by itself, if I take, say, the root, sorry, just cross that out. If I take the root w and I times it by itself, then, I'm going to have w might be r cis theta. Well, I'm going to times it by r cis theta, but we know that the way we do that is to go r times r and cis of theta plus theta, right? But the r's are 1, so you just end up with cis of theta plus theta. In other words, if we double the argument, when we go w times w, we just double the argument of w, and that'll be w squared. And that, if we go w times w, we'll triple the argument of w, and that'll be w cubed. That's what I'm trying to say. I'll just remove this here to give myself some more room. What I'm trying to say here is that if we start with w being the smallest positive, like say that's there, that's w, because 1 is a real root. It's also a complex, but it's not purely, it doesn't have any complex element, imaginary element there. W is our smallest complex root as such, with the smallest positive argument, right? And say its argument was theta. Well, then when we times w by itself, you might get one out here, for example. That's w squared, w times w. Well, it's going to have an argument of 2 theta, because that's how it works with complex numbers. You add the arguments when you multiply them, and it's still going to have the same modulus. It's still going to sit on that unit circle. And so we can times it again, and we'll get one with an argument of 3 theta, and so on. So we get these roots that are evenly spaced around the complex plane with a radius of 1 here. So we'll just need the 7 roots. So there's 1, to 3 there, 4, 5, 6, 7. So it might look something like that, with each of these being the same angle apart. And we know what that angle is too, because it's just 2 pi divided by 7, isn't it? Right? That angle there, theta, is 2 pi on 7. So that would be w to the 4, that would be w to the 5, and that would be w to the 6. We know that each of the complex roots of unity, or all the roots of unity, are evenly spaced around the complex plane, so that would be what they are: w squared, w cubed, w4, w5, w6, and w, and of course 1, because 1 to the 7 is 1. So that's answered that question in a way. Now, express them, we've done that. The next part, find the value of that. Well, if we can just express all of those somehow in terms of what we know, these roots here, then we'll be fine. Now, I might need a little bit more room, so I'll just pop a page break in here. Give me a bit more room to discuss this. First of all, we know that for z to the 7 minus 1, we can actually factorize that and say that'll be z minus 1, and then we've got our 1 plus z squared plus z cubed plus z4 plus z5 plus z6, right? And given that we know that w is actually a root of this, then we know that w minus 1 times, whoops, just get a eraser, times 1 plus w squared plus w cubed plus w4 plus w5 plus w6, we know that that is equal to 0, right? Because we're trying to solve that equal to 0. And we know w is a root, so we can sub it in and it works. And we know that w is not equal to 1 because it's the root with the smallest positive argument, and 1 has an argument of 0, right? So w is not equal to 1. Therefore, this 1 plus w squared plus w cubed plus w4 plus w5 plus w6 must equal 0. Because if you stuck w, like the value of w there, if it was 1, then 1 minus 1 is 0, and it would make the expression all be 0. But we know it's not equal to 1. Therefore, how is those two factors going to multiply together to equal 0? Only if the second set of brackets is 0, which means what I've written down at the top of this next page here must be the case. So we know that piece of information there. We also know that w to the 7 equals 1 because w is a root of z to the 7 minus 1 is 0, right? So we know that bit of information, and we know that bit of information. So we know, from that we can change that up and say, well, w plus w squared plus w cubed plus w4 plus w5 plus w6 equals minus 1. We can try and find different manipulations to suit what we need. So what we've been asked to do in this question is to find the value of 1 on w plus 1 on w squared all the way to 1 on w6. So I'll just write that down. We want 1 on w plus 1 on w squared plus 1 on w cubed plus 1 on w4 plus 1 on w5 plus 1 on w6. We've been asked to find that. Well, here's one way to do it. The number 1 is equal to w to the power of 7. See how I've circled that there, right? Look, there's various ways to do this. I might do it in a couple of ways, but I'm going to replace 1 with w to the 7, all right? So instead of 1 on w, it's w to the 7 on w, and w to the 7 on w squared, and w to the 7 on w cubed, and so on. Okay, So that's w to the 6 plus w to the 5 plus w to the 4 plus w to the 3 plus w to the 2 plus w to the 1, right? Which equals, as I said up here, I'll just put it in blue, minus 1, right? So there's one way that you could look at it. I mean, look, you could do it with brute force. You could say that, you know, you're 1 on w plus 1 on w squared plus 1 on w cubed plus all the way up to 1 on w6. You could make them with a common denominator. So on w squared, w cubed, w4, w5, w6, this would be w squared, w cubed, w4, w5, w6 plus w cubed, w4, w5, w6 plus w squared, w4, w5, w6 plus w squared, w cubed, etc. Right? So you could put it all on common denominator. And so this would be w to the 6 and 5 and 4 and 3 and 2, 20. And w to the 1, 3, 4, 5, 6, 19. And w 1 plus 2 plus 4 plus 5 plus 6, 18. Yep. And w17 and w16. So 1, 2, 3, 4, 5. And w15. All over w to the 1 plus 2 plus 3 plus 4 plus 5 plus 6, 21. Once you get it to that point, you just need to express it with powers of 7. Like this first one is w to the 14, so 7 squared, times w to the 6. That's w20. And then you've got w to the 14 times, you get plus 5. And w to the 14 times 4, and 14 times 3, all the way down to w to the 14 times w. And that's all over, that's just w7 cubed. Now w7 is 1. So square it, you get 1. So basically, this comes down to be w6 plus w5 plus w4 plus w3 plus w2 plus w, which is, as we said before, minus 1. Now, there may be other ways to manipulate that and get that answer. So it's about looking for how we can use the information given about the sum of the roots and about the actual solution.